Yeah, Ari, should we start or should we wait a couple of minutes?
So we can start at 10:40.
Okay.
Yes, sir. Mine is matching. Now I see what I did mistake, sir.
So
I think Nishan.
what was your mistake?
Sir, while putting from sir, actually I just switched the CO and H2 column in one. So
Oh,
I write CO instead of H2 and H2 instead of CO.
oh,
Sorry, sir.
yeah. I think it started because of me because I had only made a mistake in writing. Oh, it wrote CO twice. Okay, I think let's get started. Okay, Nishan, so will you tell us how you have solved?
Yes, sir.
Yeah, go ahead. I'm writing.
Sir, per pass conversion of CO is 18%.
Okay.
So amount of CO reacted.
Okay, so per pass conversion of CO is 18%. That means if 32.5 plus X of CO moles are coming into the reactor, then how much would be left?
Sir,
Yeah, go ahead, go ahead. I'm listening. I'm writing whatever you're
so
writing.
how much amount of CO reacted will be
Uh,
equal to amount of methanol formed.
right. So CO reacted would be 0.18 multiplied by 32.5 plus X. Is that what you are saying?
Yes, sir.
Okay, and the stoichiometry is CO plus two hydrogens giving us methanol. Okay, so methanol formed you are saying is 0.18 multiplied by 32.5 plus X. Okay, and
And now CO is 32.5 plus X minus these terms.
right, which is nothing but 82% of 32.5 plus X. Hydrogen.
Hydrogen will be, so twice amount of CO hydrogen will be react.
Okay, so how much hydrogen will come in stream number 4?
67.3 plus Y minus
67.3 plus Y minus
0.36
0.36 multiplied by
32.5 plus X.
32.5 plus X.
CH4 will be same.
CH4 would be same, zero point 0.2 plus Z.
Yes.
Okay, everybody okay so far? Anybody has any issues? Okay, so now all the methanol is going to be separated. So this methanol form would be 0.18 multiplied by 32.5 plus X. All right. Okay, now go ahead.
So here also same moles will be there.
All right. So here also, if you want to write in terms of gram moles, CO will remain the same, 0.82 multiplied by 32.5 plus X. Hydrogen going out would be 67.3 plus Y minus 0.36 multiplied by 32.5 plus X. Methane would be zero point 0.2 plus Z. Okay. Okay, everybody okay so far? Anybody has any doubts? Anybody has any issues? Okay, go ahead, Nishan.
So XYZ will go to recycle.
Okay, so now you are saying this stream number 8 and stream number 2, they are identical. So this would also be X, Y, and Z. Okay.
Yes, and now this 0.82 into 32.5 plus X minus X will go in purge.
Okay, so gram moles in the purge stream, if I write, stream number 6 is getting split into two streams. Stream number 8, which is recycled back, and stream number 7, which is purged. So if I look at this particular point and write a balance for the amount of CO coming in, CO coming in is 0.82 multiplied by 32.5 plus X. X is going to go back in stream number 8. So stream number 7 would contain 0.82 multiplied by 32.5 plus X minus X. Is that what you are saying?
Yes, sir.
Okay. Same way, hydrogen going in the purge would be 67.3 plus Y minus 0.36. Let me just go to the right. 0.36 multiplied by 32.5 plus X. That is what comes in at
Minus Y.
this particular point, out of which Y is going to go back as a recycle stream. Therefore, purge will contain this minus Y. And methane 0.2 plus Z comes in, minus Z what goes as recycle stream. So stream number 7 would contain 0.2 plus Z minus Z. Is that what you're saying, Nishan?
Yes, sir.
Okay. Anybody has any doubts? If you have any doubts, you can just unmute yourself and ask. Okay, go ahead, Nishan.
And sir, methane is
So this Y you can cancel straight away, and this Z you can cancel straight away. Okay, now
3.2 upon 100 is equal to
say that again. 0.2.
3.2% is equal to
Right. So this methane is contributing to 3.2%, but its total moles are 0.2. Therefore, if you write in terms of total moles, that would be 0.2 is corresponding to 3.2%. Therefore, the total moles must be 0.2 divided by 0.032. How much is this number, Nishan? Nishant, are you there?
6.25.
Yeah, 6.25. Okay. Now,
Now 6.25 is equal to addition of all these terms.
right. Now, the number of gram moles of carbon monoxide we have got, the number of gram moles of hydrogen we have got, the number of gram moles of methane we have got, and we also know that the total quantity is 6.25. So if you write that equation, 0.82 multiplied by 32.5 plus x minus x, that is the moles of carbon monoxide, plus 67.3, that y has cancelled out, minus 0.36 multiplied by 32.5 plus x, that is the moles of hydrogen, plus moles of methane, zero point 0.2. These three things put together must be 6.25 gram mole. So we have one equation and the only unknown is this x. So solve for x, and Nishan, what is the value of x?
141.
141. 141 point something or 141?
141.1.
141.1. Okay. Right. So now we have got this value of x, right? That we have got this value of x, we have got this value, we have got this value, we have got this x, we have got this x, we have got this x, we have got this x here, we have got x here. Okay. Anybody has any doubts so far? Anybody has any doubts so far? One more thing, if you want to check, right? If you take this green control volume, if you take this green control volume as the whole plant, oops, I should not draw it here, I should draw it here. If we take this green control volume as this whole plant, right, 0.2 gram moles of methane are coming in. There is no methane reacting in this control volume. There is no methane going out anywhere else except this purge stream, stream number 7. So this methane going out must be 0.2 gram moles. And 0.2 gram moles corresponds to 3.2 mole percent. So total moles must be 6.25. You could have got that straightforward without even writing any of these things. Anybody has any doubts? Anybody has any issues? Anybody around?
Yes, sir.
Yes, sir.
Yes, sir.
Hope people are around. Okay. Okay, Nishan, go forward.
So now we will find mole percent of the purge stream.
So we have got now x. So now you can substitute that particular value of x and get the gram moles here. That's what you are saying?
Yes, sir.
Okay. So do that and tell me the values. So, oops, sorry. So methane would be 0.2. Okay. Hydrogen would be
4.8.
4.8. And carbon monoxide would be
1.25.
1.25.
25.
Okay, go ahead. If you have doubt, please unmute yourself and ask.
So
Yeah, go ahead.
mole percentage are 19.9,
19.9,
76.9,
76.5,
99,
oh, 76.9, 76.9, okay, and 3.2.
3.2.
Right. Okay, now
Now, sir, we will substitute these mole percentage values in table number 6.
in which stream? Stream number 6.
6, sir.
Right. Why is that? Because if you look at this particular point, the stream 6 that is coming in is split into two parts, stream 8 and stream 7. So whatever is the composition in terms of mole percent or weight percent or volume percent, I must have the same composition in stream 7 and stream 8 and stream 6. So stream 8 will also contain 19.9 mole percent carbon monoxide. Stream 8 will also contain 76.9 mole percent hydrogen, and stream 8 will also contain 3.2 mole percent of methane. And same way, if I look at stream number 6, the mole percent in stream number 6, let me write it here. Stream number 6 will also have 19.9 mole percent of carbon monoxide. It will have 76.9 mole percent of hydrogen, and it will have 3.2 mole percent of methane. Okay, now go ahead.
So now we will calculate the moles of CO first.
Right, so X value we have already got. So we can substitute that X value here, and we can get the moles of carbon monoxide in stream number 6. All right, so tell me what is that value?
142.36.
142.36. Okay, now?
So now we will get for H2.
Right, so now the hydrogen and carbon monoxide must be in the proportion 19.9 and 76.9. So if you take this ratio 67.3 plus Y minus 0.36 into 32.5 plus X, and X of course we have already got. X is 141.1. So that is the moles of hydrogen, and moles of carbon monoxide are 142.36. They must be in the same ratio as the mole percents we have already got, 76.9 divided by 19.9. Okay, and therefore we can get a value of Y. Is that what you are saying, Nishan?
Yes, sir.
Okay, so what is the value of Y?
541.8.
541.8. Okay, go forward. So we have got X, we have got Y.
The same procedure we will follow for
Same way,
CH4
we
moles.
will get the value of Z. The moles of methane, 0.2 plus Z divided by moles of carbon monoxide, 142.36, must be in the same proportion, 3.2% and 19.9%. So this will allow us to calculate the value of Z, and Z would be
22.57.
22.57. Okay, so we've got X, we've got Y, we've got Z. So that means we know everything now. We know everything everywhere. Have we solved our problem? Anybody? Yes.
Now, overall convergence.
Right. So now the percent overall conversion, if you want, that is across the whole plant, that is across this green control volume. What comes in, carbon monoxide coming in is 32.5. Carbon monoxide going out of this green control volume, overall plant, is 1.25. Right. So that is how much carbon monoxide has reacted overall. So percent conversion is 32.5 minus 1.25 divided by 32.5 multiplied by 100, and you will get something like 96%. Okay. Couple of points to note. The per pass conversion of CO was only 18%. The overall conversion is 96%, right? If I had not recycled, we would have wasted lot of carbon monoxide and lot of hydrogen. By recycling, we have been able to increase the utilization from 18% to 96%. Do you realize that? Had we not recycled, we had not recycled after the condenser, had we vented all the gas, lot of gas, 82% of 32.5 would have gone out as unreacted gas. So by recycling, we are allowing better utilization. We have utilized 96% of whatever comes in 32.5 because all the rest is kept on recycling. What goes out is only 1.25. Do you agree with this? Do you disagree? Anybody else? Do you people agree, disagree? What are you saying? Anybody saying something?
Yes, sir, I agree.
Yes, sir.
Only 2 people have agreed. Other 51 are still not saying anything.
Excuse me, sir.
Yeah.
So the purge stream can be used to make methanol again.
No, the purge stream, we are not recycling back purge stream. We have taken out the purge stream so that the methane is building up to not more than 3.2%. I mean, if we allowed methane to build up to 3.5%, then I could have purged a little quantity, I could have recycled more. This percent conversion would have gone up from 96 to maybe 97, 98.
Okay,
The
sir.
constraint that we have been given is that the methane going out should be 3.2%. To that extent, we are allowing recycle. Had we allowed it to be more than 3.2%, maybe 4%, 5%, 6%, our percent conversion would have increased even, overall conversion would have increased even more. Is that okay?
Yes, sir.
Okay, so right now we have got up to 3.2% and therefore we need to purge some amount. We need to purge 6.25 moles containing 1.25 moles of carbon monoxide, and therefore we are getting 96% overall conversion. Okay, that is one point to note, how recycling helps to have a better utilization of carbon monoxide. Had this number 3.2, suppose instead of 3.2, maybe only 2.5 was allowed, we would have had to recycle less, we would have had to purge more, and therefore the percent conversion would have reduced. It would not have been as much as 96, it may have been 90, 89, 88, whatever. But still, it is significantly more than the per pass conversion, which is 18%. Hardik, is that okay?
Yes, sir.
Okay. Second thing to note is that the amount of recycled gas, CO and hydrogen and methane. CO was 141 point something, 141.1, I think. Hydrogen was 541.8. Methane, what was the value? Some 22 something, 22.57. These are significantly higher than these incoming moles. Right? That's okay because we are allowing plant to operate at steady state. Another thing you will notice is that the ratio of carbon monoxide to hydrogen in the fresh feed gas is different from the carbon monoxide to hydrogen ratio in the recycled gas. Right? Because we are allowing methane to build up, hydrogen is in excess more than what is required for stoichiometry, 1:2, and therefore the amount of hydrogen being recycled is more than the amount of carbon monoxide being recycled ratio wise. So we are not, we have got an answer based on this 3.2%. But if you want to solve this problem again for yourself, if you think about instead of 3.2% methane in gas leaving the condenser, suppose instead of 3.2, suppose we make it as say 2.8, then you can redo the whole problem, see how your answers change. Or instead of 3.2, suppose I make it 3.4, you can again redo the whole problem and see how things change, how the overall conversion changes, how the recycle amounts change, how the flows and how the total gram moles of each of these components change. Right? So that is something that you should do for yourself. Take different values and see for yourself how these numbers are changing, how 96% can be reduced, can be increased, depending on how much methane is allowable in the gas stream going out from the condenser or coming in. Finally, all that has to come in to the reactor, the amount of carbon, amount of methane coming into the reactor. Okay, can we go forward? Can we go to the next problem? Is there any doubt? Any other question?
No, sir.
Anything we need to explain? Anything we need to discuss? Can we go to the next problem?
Yes, sir.
Anybody has any other issues? Right from day one. Can we go to the next problem?
Yes, sir.
Okay.
Yes, sir.
Yes, sir.
Okay. So here is a next problem. We had talked about ammonia synthesis. So imagine that there is a fresh feed. This fresh feed contains nitrogen, hydrogen. See, in the simplified problem, we had, where was that? Yeah, in the simplified problem, we had only talked about nitrogen and hydrogen in the ratio 1:3. That's what we wanted, right? But this air that is going to be supplied is going to contain several things along with this nitrogen and oxygen. One of the impurity coming up along with the air that keeps on accumulating in the process is argon. So imagine that we have this fresh feed which contains, let's say, 24.57 if we think in terms of mole percent. 24.57 mole percent nitrogen, 75.16% hydrogen, and 0.27% argon. Okay. So this fresh feed, along with some recycled feed, we will come to that goes to this reactor. It's a high temperature, high pressure reactor, nitrogen plus hydrogen, giving us ammonia. Everything is in the gas phase. All the nitrogen does not react. So nitrogen, hydrogen, argon will still be there. Argon is an inert, and ammonia will be formed. Any thoughts about how do we separate ammonia?
The
Pardon?
Liquefy.
Liquefy. Okay, so cool and condense. We'll have to cool below the dew point of this incoming gas. Recall what is meant by dew point. Ammonia will condense in the liquid form. Nitrogen, hydrogen, argon will go unreacted, uncondensed. Again, like last time, because we are separating out liquid ammonia, the gas going out from the condenser will be saturated in ammonia. Suppose this is at a temperature of 50 degrees centigrade, then this gas that is going out from the condenser, the partial pressure of ammonia in this gas going out from the condenser will have partial pressure equal to vapor pressure at 50 degrees centigrade of ammonia. But just to make your life simple, we are neglecting that just now. We are going to say that all the ammonia condenses out.
So,
Yes,
if we condense it to a temperature where the vapor pressure is negligible,
correct. Correct, correct. I mean, yeah, I mean, so right now I'm just saying 50 degrees centigrade, but suppose I cool it down to not 50 degrees centigrade, suppose I cool it down to 20 degrees centigrade, then partial pressure will be equal to vapor pressure at 20 degrees centigrade. And the lower I keep on cooling, the lesser and lesser amounts of ammonia will be present in this gas going out of the condenser, right? But it is never going to be zero, because vapor pressure is not going to be zero anytime unless I go to 0 Kelvin, right? Which is not possible. So there is going to be some finite amount. Right now we are neglecting that finite amount. Is that okay, Arya?
yes, sir.
Okay. Now, if I recycle this gas as such, then there will be a problem that argon comes in, but argon does not react. So all the argon will keep on accumulating, and therefore we must be able, or we must be able to control the amount of argon that remains in the combined feed, right? We are calling it this as fresh feed, we are calling this as combined feed. This is our recycle. We are purging some amount of gas so that the argon that builds up in the loops at steady state is maintained at a desirable level. So if nitrogen, hydrogen, argon are recycled, the recycled gas also will have nitrogen, hydrogen, argon, and that will mix with the fresh feed. The combined feed will go to the reactor. Part of the ammonia, part of the nitrogen will react, ammonia will form, unreacted nitrogen, unreacted hydrogen, unreacted argon, which is inert, will go out from the reactor, goes to condenser, right? Let's just give some names to different streams. Let's call this as stream number 1, let's call this as stream number 2, let's call this as stream number 3, let's call this as stream number 4, let's call this as stream number 5, let's call this as stream number 6, let's call this as stream number 7. Right? And recall how we are going to do the recycle problems. We are going to break this recycle stream. We are going to say that it is equivalent to 2 different streams. So stream number 7, we said is a recycle stream, but we are going to break that and we are going to say that the stream number 7 is different from stream number 8, which is recycle, coming back mixing with the fresh feed. But in reality, we know that stream number 7 and stream number 8 are one and the same. So the moles as well as mole percents or weight percents or any other composition measure that we have for stream 7 and stream 8, they are going to be identical. Okay, so this stream number 7 also is going to contain nitrogen, hydrogen and argon. The purge stream also is going to contain nitrogen, hydrogen and argon. Let me just write that. Let me just write that slightly ahead. Let me just write that slightly ahead. Nitrogen, hydrogen, argon. Okay, is the problem description clear to everybody? I will give you some more compositions. In the combined feed, hydrogen in terms of mole percent, hydrogen is 79.52. Okay. In the gas going out from the condenser, if we write in terms of mole percent, hydrogen is 80.01. Okay, these are the compositions that I know. Here is what you need to find. Okay. Find quantities and compositions of all streams. You can take basis as 100 moles of the fresh feed. So if you want to write in terms of moles, we can take basis as 100 moles of the fresh feed. Right. Second, for pass conversion, of nitrogen and hydrogen in terms of percent and in terms of percentage overall conversion. Of nitrogen and hydrogen. Okay, let's do this problem. If you have any doubts, you can always unmute yourself and ask. We have just given different numbers to different streams, 1, 2, 3, 4, 5, 6, 7, just for our convenience, just so that we can talk about different streams. Recall the general way of solving these recycle problems. We have broken the recycle stream into two streams, stream number 8 and stream number 7. Because we don't know anything about stream number 8, we are simply going to assume in terms of gram moles, X moles of nitrogen, Y moles of hydrogen, Z moles of argon, and then we are going to solve the problem, then everything we know about the fresh stream, we know about the recycle stream, write material balance and get combined feed, and then go forward. And then at the end, we are going to say that stream number 7 and stream number 8 are identical. They are one and the same. Anybody has doubts about the problem? Anything that was not clear in the description? Anything you want me to repeat from the problem description? No, nobody wants to. Nobody has any doubts about the problem, about the description. If you've got an answer, you can tell me. If you just tell me X, Y, and Z, everything will fall in place. How come you're all so quiet today? No questions? Who? Anybody wants to volunteer? Smith, are you there? Would you like to volunteer?
Sir, I'm solving.
Okay, okay.
Hello, sir.
Yeah,
Sir, in the fresh feed, it is mole, right? Not mole percent.
it is mole percent, but because we have taken basis as 100 gram moles of the fresh feed, mole percents and moles become the same.
Okay, sir.
This is mole percent, but because we are taking basis as 100 gram moles of fresh feed, so moles and mole percents are the same. I should be saying gram moles. Okay, anything, any other point? Anybody has any other doubts? Anybody's absolutely stuck? Abhay, are you there? Aditi, are you there?
Yes, sir.
Solving?
Yes, sir. Trying.
Okay. Ankush, are you solving?
Yes. Yes, sir.
Are you solving?
Yes, sir.
Are you stuck? Any hint?
So, so
No answer, Ankush. Are you solving, not solving?
solving, sir. Just
Okay.
trying.
Prashasti, are you solving? Are you there? Okay. Our overseas friend, Edith, are you there?
Yes, I'm solving.
Okay. Any doubts?
No, not yet.
Okay. Sohan, are you there?
Yes, sir.
Solving?
Yes, sir. Trying.
Okay.
Hello, sir.
Yeah.
Sir, actually, I'm stuck somewhere.
Okay. Where are you stuck?
Sir, we can say like at the start only, yes. Sir, I have just written some obvious things. Yeah. I have not accepted calculated anything.
No, it is not, your voice is not very clear. Can you speak little loudly and slowly?
Yes, sir. Sir, I'm stuck at the start only, sir. I have just written some obvious thing, not calculated anything.
So, did you assume X, Y, and Z?
Yes, sir.
Okay, so based on this X, Y, and Z now, you can write stream number 2. You can write moving
Yes, sir.
stream number 2.
Yes, sir. That I've done.
Okay, once you write for stream number 2, can you write for stream number 3?
Sir, only argon we know, sir.
Pardon?
Sir, only argon we know, sir. Percentage conversion we have to calculate.
Yeah, but it's an unknown, right? So you can assume some one more unknown, X, Y, Z, and P if you want, X, Y, Z, Q.
Okay, sir. I'm fine.
It is to be found, so I don't know that. So we can assume some variable.
Okay, sir.
Then you can write stream 3, then you can write stream 4, then you can write stream 5, stream 7, stream 6. Use the data that in the combined feed hydrogen is 79.52 mole percent. In stream number 5, leaving the condenser, it is 80.01%. Is that okay?
Yes, sir.
Smith, how far have you come?
Sir, I am stuck somewhere.
Where? Where are you stuck?
Sir, I assume four unknowns.
Okay. Which ones? X, Y, Z, and
N. The
N. N is what?
amount reacted of nitrogen.
Okay, so will you be able to tell us something about um, uh, do you want to solve, or do you need more time to solve?
Sir, I need more time.
Okay, okay. How much time? 5 minutes, 6 minutes, 10 minutes?
5 minutes, sir.
Okay, okay. We'll wait. Should we solve? Do people need more time?
Sir, 2 minutes more, sir.
Okay.
Sir, can I tell the answer?
Yes, yes, Nishan.
So X is 102.67.
X is 102. Okay. 102 point.
67.
Okay.
Y is 711.25.
Correct.
And Z is 75.03.
Yeah.
And sir, per pass conversion of nitrogen is 19.1,
Yeah.
of hydrogen is 9.2,
Yeah.
and overall conversion of nitrogen is 98.5,
Yeah.
and hydrogen is 96.6.
Yeah. If XYZ is correct, then everything else will be correct.
Okay.
We'll just wait for Smith to tell us his solution. Smith, do you want to explain?
Sir, I got Y as same as Anishant,
Yeah.
but I'm stuck in solving X and Z.
Okay, okay. So what we will do is you tell us how you got Y, how you have calculated it so far.
Yes, sir.
Okay, Smith, go ahead.
Sir, in the combined feed, the mole percent of H2 is 79.52,
Right. So 79.52. Okay.
and gram moles is 75.16 plus Y.
Right.
So we can calculate the total gram moles of combined feed.
Okay.
It is coming out to be 94.52 plus 1.2575.
1.257 Y. Okay. So everybody's got up to here so far. Anybody has any doubts? You can always ask. Unmute yourself and ask. So because hydrogen is 79.52, and if you stream number 2 will just be addition of stream number 1 and stream number 8. So hydrogen in stream number 2 would be 75.16 plus Y, and 75.16 plus Y correspond to 79.52 mole percent, and therefore the total must be 75 total moles. Let me write that here: total moles in stream number 2 would be 79 point, sorry, not 79, 75.16 plus Y. That is the moles of hydrogen that correspond to 79.52%. So the total must be 75.16 plus Y divided by 0.7952. And then if you just simplify this, this would come to 94.52 plus 1.257 Y. Smith, is that what you are saying?
Yes, sir.
Okay. Anybody has any doubts up to this? Okay. Go ahead, Smith.
Sir, then in the recycle stream
Right.
number 8,
Right.
we have 80.01 mole percent of H2.
Ah, very smart. So this also you are saying that in terms of mole percent, this H2 is 80.01 mole percent. Okay.
Sir, then total moles of the recycle stream is 1.2498 Y.
1.2498. So shall we just say 1.25 Y?
Yes, sir.
Okay. Okay. So okay, go ahead. Go ahead.
Then 1.25 of the recycle stream and 100 gram moles of fresh feed is equal to 94.52 plus 1.257
Ah,
Y.
so again, you are writing the addition of stream number 1 and stream number 8, giving you stream number 2. So 100 is the total moles of stream number 1. 1.25 is total moles, 1.25 Y is the total moles of stream number 8. And therefore the total moles of stream number 2 must be 100 plus 1.25. But we also know that from the hydrogen composition it is 94.52 plus 1.257 Y, and therefore we can solve for Y. So what is the value of Y?
711.69.
711.69. So shall we just say 711.7?
Yes, sir.
Okay. So this Y we have already got, that is 711.7, right? Hydrogen in the fresh feed would be 75.16 plus that 711.7 together would be the hydrogen in the combined feed. So tell me that value, 75.16 plus 711.7. Smith?
786.86.
Okay, 786.86. And you can tell me the total also, 94.52 plus 1.257 Y.
$989.48.
989.48. Okay. Okay, anybody has got up to here, and total moles of the stream number 8 also you can tell me. 1.25 times Y.
889.62.
Total, let me write the total here. Total was 1.25 Y, and Y is 711.7. So the total would be
889.62.
889.62. So we have got a value of Y, and immediately we are substituting that value of Y so that we leave our number of unknowns to as less as possible. Okay, go ahead, Smith. Anybody has doubts up to this point? Anybody has doubts up to this point? Okay, go ahead, Smith.
So could you explain it? So how did we get 1.25 Y?
How did we get 1.25 Y?
Yes, sir.
Smith, how did we get 1.25 Y?
Sir, by in recycle stream, the mole percent is of H2 is 80.01
Correct.
and gram moles is Y. So
In the
total
recycle stream, Hardik, in the recycle stream, hydrogen moles were Y and they corresponded to 80.01 mole percent. Why 80.01 mole percent? Is because in the stream number 5 it is 80.01 mole percent. So stream number 6 also must have mole percent. If we write from stream number 6, that also must be 80.01. If we write for stream number 7 mole percent, that must also be 80.01. And because stream number 7 and stream number 8 are actually the same, we have just cut it into two parts just for our convenience, and therefore in stream number 8 it also must be 80.01%. So total must be Y divided by 0.8001, like just point that just 1.25 Y. Hardik, is that okay?
Yes, sir. Thank you, sir.
Yeah. So stream number 7, stream number 5, stream number 6, stream number 8, they will all have the same composition, because it is stream 5 that is getting split into stream 7 and stream 8, and stream 7 and stream 8 are one and the same. We are just, for our convenience, we are just saying they are two different streams. Okay, Smith, go ahead.
Sir, I'm stuck here.
Oh, you are stuck here.
X and Z.
Oh, okay. So you can eliminate one more variable. You can eliminate Z as well, right? Because the total moles of the recycle stream, stream number 8, we have already got. It is 889.62. Out of which 711.7 is hydrogen, X is nitrogen. So argon would be 889.62. Let me just, the number space is little less. So argon, moles of argon in the recycle stream, this would be 889.62 minus 711.7 minus X. We can eliminate one more unknown and keep everything in terms of X. Is that okay?
Yes, sir.
So just simplify this. 889.62 minus 711.7.
$177.9.
So 177.9 minus X is the argon. So nitrogen, now if you write a balance for this point, stream number 1 and stream number 8 are mixing to give you stream number 2. So the gram moles of nitrogen would be 24.57 plus X. Gram moles of argon would be 0.27 plus 177.9 minus X. Is that okay?
Yes, sir.
Okay. Now, we don't know, there is no other way we can evaluate this unknown X. So let's go forward to stream number 3. Stream number 3, argon is not going to react. So argon in terms of gram moles, if you write for stream number 3, it is going to remain the same, 0.27 plus 177.9 minus X. Okay. Now we can say something about percent per pass conversion. That's not known to us. Okay, so we can assume some value, assume some variable. We can assume some variable as number of moles of nitrogen reacted or number of moles of hydrogen reacted. and then we could write, let's assume this variable as some p if you want. So then we can write nitrogen in terms of p, hydrogen in terms of p, ammonia in terms of p. So now we will have two unknowns again, p and x. And now you can go forward from stream 3 to stream 4 to stream 5 to stream 6 to stream 7. Smith, is that okay?
Yes, sir.
Will you try that now?
Yes, sir.
Okay, try. Dharmik, you had a question?
No, sir, I was saying the same thing.
Sir, I have a doubt.
Yes, Riya.
How can the total number of moles be recycled that were recycled be greater than the total number of moles being input? Is that possible?
Yeah, I mean, we had the same thing in the previous problem, right? We had 100 moles in the fresh feed, and the number of recycled moles were significantly larger. They are operating at steady state, right? So I can have more recycle than fresh feed.
Yes, you said that.
Suppose in your house, suppose some guests were going to come, your parents cook food for 20 people, but suppose these guests don't turn up. So next day, how much your mother cooks? You have food for 20 people being carried forward as recycled from the previous day. You only cook very little for the next day, right?
Yes, yes.
It's like that. So fresh feed is what you're cooking for the fresh new day. Recycle is what you have carried forward from the previous day. There's no connection. It is only dependent on how much composition of argon is allowed or I can tolerate in the reactor. Okay, Riya?
Yes, sir.
In the days of Corona, there are no guests and nobody wants to go anywhere to anybody's house. That's a different story. Smith, you are trying, right? Right?
Yes, sir.
Yeah, go ahead. Continue. Try. So we try to keep variables as less as possible, unknowns as less as possible. We had to introduce one more, so now it is x and some p as one more unknown. Don't forget the stoichiometry. Nitrogen and hydrogen react to give you ammonia. Don't forget the stoichiometry. If I take 1 mole of nitrogen and 3 moles of hydrogen, I will get 2 moles of ammonia. Don't forget the stoichiometry. Any answer, Smith?
No, sir.
Oh. Solving?
Sir, I'm getting stuck here.
Stuck where?
Sir, in the purge and recycle stream.
Okay, let's go little forward then. Okay, what did you assume? Nitrogen reacting as P, hydrogen reacting as P, or what did you assume?
Nitrogen reacting SP.
Okay, so assume that gram moles of nitrogen reacted in the reactor is some P moles. So then we can write balance across the reactor, across our this control volume. Okay, so nitrogen would be 24.57 plus X, that's what comes in, minus P reacts. So what goes out in stream number 3 would be 24.57 plus X minus P. Hydrogen would be 786.86 minus how many P?
3P.
3P, right? So don't forget the stoichiometry. 1 mole of nitrogen reacts with 3 moles of hydrogen, giving us 2 moles of ammonia. So the ammonia formed would be 2 times P. So all the ammonia is removed here. So in terms of gram moles, ammonia would be 2P. Okay. Now let's go further. Let's go towards the stream number 5. Stream number 5, in terms of gram moles, if we want to write, it would be 24.57 plus X minus P. Hydrogen would be 786.86 minus 3P. Argon would be 0.27 plus 177.9 minus X, right? All the ammonia is removed. Now, in stream number 5, we also know that hydrogen is 80.01%. So if I write total, how much would be total? Total, can you write, Smith? Add up all these things. Add up this plus this plus this. Can you write the total? 24.57 plus X minus P plus 786.86 minus 3P plus 0.27 plus 177.9 minus X.
Sir, 989.6
Okay, 989.6
minus 4P.
minus 4P. Now, don't we know that in stream number 5, mole percent of hydrogen would be 80.01? So can we not say that 786.86 minus 3P divided by 989.6 minus 4P would be 0.8001? Does that help you to get P? Or you get 0 equal to 0? Or 1 equal to 1, 100 equal to 100? Or does it help you to get a value of P? Smith,
Yes, sir.
have you got P?
No, sir.
Can you get from now? From this equation now?
Yes, sir.
Okay, get. P is, somebody solve and tell me what is P.
247.25.
247.
24.1.
Yes, sir.
24.1.
Yes,
Yeah,
24.1.
Yes, sir. Sorry.
24.1. Right. So we had introduced one more unknown P, but we have also got a value of P. So this P we know, this 3P we know, 2P we know, so 2P we know, this P we know, this P we know. Okay, now can we go forward? Total we know.
Yes, sir.
Now can you go forward and get a value of X?
Yes, sir.
Once you got a value of P, immediately substitute and simplify. So don't keep it as 2P. 2P would be 48.2. 48.2. Immediately simplify. 24.1. 3P. 72.3. 4P. 96.4. Simplify. 24.1. 3P. 72.3. Keep the number of unknowns as low as possible. We still have X as unknown. Are you getting Smith or should we solve?
Yes, sir. Getting.
Oh, Any answer for X, Smith?
116.1.
Okay. 116.1. Anybody else has any other answer? Nishan, what was your answer? I forgot what you told.
102.67.
102, and this is 111. Okay. Yeah, Nishan, just check your value. Maybe just round off error.
Okay, sir.
102 seems to be correct. Anyway, can we go forward? Anybody has any doubts?
Sir,
Yeah,
102.74.
yeah, 102 point something. Right, so once you get the X value, basically you got everything. So then you can find out the per pass conversion of nitrogen and hydrogen. Remember, the per pass means across the reactor, and overall means across the whole plant. That means if I take this whole plant as a control volume, right? That is the meaning of per pass and overall. Okay, shall we go to the next problem? Shall we go to the next problem?
Yes, sir.
Yes, sir.
Okay, so here is the next problem. Okay, we have talked about dryers. So there is a dryer. So the dryer, some wet solids are going to come, right? So let's say wet solid, let's say our product is P and moisture. So I have P and water, right? So P and water if you want. And let's say in terms of weight percent, it is 40 weight percent water, 60 weight percent P. P is our product. Let's be a drying. Remember our crystallization, filtration, drying problem. And then you get solids which are dried solids. So we will still have P, we will still have some water. So in terms of weight percent, let's say it is 2 weight percent is our product. P is 98%, only 2% water. So one of the ways in which we are going to dry is to supply hot air, right? Do you remember the problem for the dryer that we did? Milk dryer that we did, do you remember? We supplied hot air.
Yes, sir.
And this hot air was going to contain very little moisture, and therefore it can, or very little water, and therefore it can pick up the water from the solids. Okay, so let's say this hot air, we want the temperature to be 60 degrees centigrade, and the dew point temperature, we want it to be 30 degrees centigrade. Okay? So the air going out of the dryer, this air going out of the dryer will obviously be cooler than 60 degrees centigrade, and it will have more humidity. Do you agree with that? Yes, no?
Yes, sir.
Right. So we don't want to waste this air. So what we will do is we will take some part of that air and we would like to recycle part of that air. Right? We would like to recycle part of the air. So suppose this air going out of the dryer, let's give some stream numbers. Let's call this as stream number 1. Let's call this as stream number 2. Let's call this as stream number 3. Let's call this as stream number 4. Let's call this as stream number 5, 6, right? So obviously stream number 4 is going to be air which is cooler than 60 degrees centigrade, and it is going to have more moisture content, more humidity, more kgs of water vapor per kg of dry air, right? So if we recycle it as such, we are obviously going to need some kind of fresh air. So we will mix the recycled air with the fresh air and then send that mixture to the dryer as stream number 3. So we got 1, 2, 3, 4, 5, 6. So let's call this as stream number 7. Let's call this as stream number 8. So fresh air, let's say fresh air is at a temperature of 20 degrees centigrade and wet bulb temperature of 10 degrees centigrade. So imagine that stream number 7 is at 20 degrees centigrade, wet bulb temperature of 10 degrees centigrade. The stream number 6 or 8, whichever is coming from the outlet of the dryer, is going to be cooler than 60 degrees centigrade. So the temperature of this stream is going to be less than 60 degrees centigrade. Temperature of this stream is going to be less than 60 degrees centigrade, right? Temperature of this stream number 8 is going to be less than 60 degrees centigrade. So I can't mix a stream which is at a less than 60 degree temperature, 20 degree temperature, and then expect to get a mixture of 60 degrees centigrade air. Do you agree with that? Stream number 7 is going to be less than 60 degrees. Stream number 8 is going to be less than 60 degrees centigrade. So if I mix stream number 7 and 8, there is no way I am going to get stream number 3, which is going to be at 60 degrees centigrade. Do we agree? Do we disagree?
Yes, sir. I agree.
Right. So obviously,
Yes, sir, I agree.
I would need stream number 8, which is having temperature more than 60 degrees centigrade. So what we will do is this stream number 6, we will not recycle directly. We will heat it up in a heater, maybe electric heater, and then we will call it as stream number 8, and then that stream number 8 now will have a temperature more than 60 degrees centigrade. So then if I mix it with stream number 7, then I will get stream number 3, which is having temperature of 60 degrees centigrade and dew point of 30 degrees centigrade. I know something more about the process. What do I know? This purge air, purged air, I know something about this. This is at a temperature of 55 degrees centigrade and percent RH equal to 90. Okay. Assume that total pressure is 760 mm Hg throughout. Throughout means all streams. Okay, is the problem description clear to you? I have a fresh air stream which is at 20 degree centigrade temperature, 10 degree centigrade wet bulb temperature. I mix that with recycle stream which is hot, stream number 8. I mix them together. Combined air is at stream number 3, is in stream number 3. Temperature is 60 degrees centigrade, dew point is 30 degrees centigrade. That is going to go to dryer where the solids are going to get dried. Air coming out of the dryer, stream number 4, is going to be obviously cooler than 60 degrees centigrade and more humid. That air, stream number 4, is partly purged and partly recycled through a heater so that its temperature can be increased. Is that okay? Is the problem description okay with everybody? Yes, no?
Yes, sir.
So let's assume that basis we want is 1 kg of the wet product. Oops, sorry, 1 kg of wet product. Why is that happening? Right, so we are taking basis as 1 kg of wet product, kgs if you want to write. So that will be 0.6 kgs and 0.4 kgs. Total is 1 kg. So that's our basis. I would like you to calculate quantities and compositions of all air streams. So if it's an air stream, you can just tell me the kgs of water vapor per kg of dryer. That's what we would mean by composition. Is the problem description okay? Anybody has doubts about the problem, about what is to be found? Somebody say something. Yes, no.
No, sir.
Do you have a doubt, Hardi? Are you clear what is to be found?
No, sir. Yes, sir.
Anybody has any doubts about what is to be found? About information given?
No, sir.
Shall we stop here for the day? Would you be able to solve this problem over the weekend?
Yes, sir.
Sir,
We
is
can.
recycle and purge
Yes, sir.
included in midterm?
Yeah, Ria, go ahead. Huh?
Is recycle and purge included in the midterm?
Recycle and purge, how different is it from any of the problems? It is just material balance, right?
Yes, sir.
Sir, what is the flow rate of the air?
Praveen, what are you asking?
The